The nightmare scenario for 3I Atlas sounds like fiction until you pause to consider it. What if this object is not departing at all? What if its sweeping hyperbolic arc is less an escape trajectory than a deliberate braking maneuver, carried out with technologies invisible to our instruments? Envision a civilization so advanced that imitating the clockwork of celestial mechanics is trivial, capable of seeding the skies with probes disguised as comets, asteroids, even the rubble of ordinary space. Atlas's unprecedented velocity and anomalous chemistry may not be fingerprints of exotic geology, but of deliberate design. As it nears perihelion, unseen systems could be stirring, aligning for the next stage of whatever mission brought it here. Tonight, we follow the path where natural explanations falter and cosmic suspicion takes hold. The real question is not whether Atlas departs, but whether we will recognize the moment it chooses to remain. Part 1. Is 3I Atlas a threat? On the 1st of July 2025, the Atlas telescope in Chile spotted something extraordinary. A faint moving point of light, sliding against the fixed tapestry of stars. Its orbit was not elliptical, not bound to the sun as every native comet and asteroid island. It was hyperbolic. That single mathematical clue meant only one thing. The object had come from elsewhere, from beyond the gravitational grasp of our solar system. Astronomers designated it 3I Atlas, formerly C, divided by 2025 N0. It became only the third confirmed interstellar object in human history, after Oumuamua in 2017 and 2I Borisov in 2019. A rare visitor from another star, rushing through our neighborhood before vanishing again into the dark. But unlike its predecessors, Atlas quickly took on a symbolic weight far beyond its icy nucleus. Its arrival sparked questions that stretched into speculation, even paranoia. What if this third messenger was not just another frozen shard, but a test of how we understand intelligence, purpose, and coincidence itself? The orbital facts were comforting in their precision. Atlas's eccentricity, greater than 1.0, marked it unambiguously as unbound. Its inbound vector pointed back to the constellation Lynx. It would swing around the sun at perihelion on the 29th of October, traveling over 130,000 miles per hour, fast enough to cross the continental United States in less than 3 minutes. Afterward, it would recede forever into interstellar space. The geometry was clean, the math elegant, and yet beneath that certainty lay a deeper unease. What if the true, worst-case scenario had nothing to do with impacts or collisions, but with what the object might force us to confront about ourselves? From the standpoint of planetary defense, there was no danger. At its closest approach in mid-December, Atlas would still be 1.8 astronomical units from Earth, 270 million kilometers, nearly twice the Earth-Mars distance at their closest alignment. NASA issued statements swiftly and unequivocally. 3I Atlas posed no threat. It was a natural comet, not an artificial craft. The agency's language was careful, almost clinical. But outside those measured press releases, speculation flourished. If an object could travel from another star and arrive here, what else might be possible? Could interstellar wanderers ever be more than random debris? Could they, in some scenarios, be intentional? The observations themselves revealed a complex picture. Hubble's instruments detected classic cometary behavior, sublimating ices, forming a glowing coma as solar radiation heated the surface. On the 6th of August, the James Webb Space Telescope captured detailed spectra. The results startled astronomers. Unusually high concentrations of carbon dioxide, a chemical fingerprint not seen in solar system comets. That single anomaly pointed to formation under conditions alien to anything we knew. The object was not artificial, it was chemical, it was geological, and yet its chemistry forced us to admit how little we truly knew about what the galaxy might create. Ground-based telescopes across the globe joined the vigil. Arrays of radio dishes scanned the frequencies where artificial signals might hide. They found only silence, broken by the broad natural emissions typical of cometary comet. The absence of signal reassured the cautious. The coordination of so many observatories in Europe, Asia, the Americas demonstrated modern astronomy at its best: international, transparent, collaborative. Together they confirmed both the interstellar origin and the harmless trajectory. And yet, the silence itself left room for imagination. If Atlas were more than a comet, would we know? Would we even recognize the signs? Statistical studies tell us that the galaxy must be teeming with such visitors. Planetesimals ejected during planetary formation, shards of comets torn loose by gravitational encounters, relics cast adrift for billions of years. Most will never cross our path. A tiny fraction will pass through the inner solar system, each carrying whispers from distant stellar neighborhoods. Oumuamua had startled us with its shape and unexplained acceleration. Borisov reassured us with its perfect cometary normalcy. Now Atlas added a third data point. Each interstellar object is a sample of the galaxy, a clue to conditions far from home. But as the catalogue grows, so too does the temptation to speculate. If debris is everywhere, could messages be hidden among it? If natural wanderers are common, could intentional ones disguise themselves in plain sight? The Guardian called Atlas a cosmic curiosity, not a catastrophe. That framing carried truth. The object was no doomsday rock, no harbinger of collision. It was a reminder that the universe is restless, that fragments from distant stars routinely cross paths with our own. It underscored connection. We are not an isolated system sealed off from the galaxy, but part of a dynamic exchange of matter across unimaginable scales of time. And yet, the real mystery may not be what Atlas is, but what it obliges us to imagine. What do interstellar visitors mean for how we think about life, intelligence, and purpose? If comets can cross light years, why not probes? If debris can survive billions of years, what about artifacts? Each discovery teaches us more about astrophysics, but also forces us to confront the edges of our ignorance. The line between science and speculation is sharp, but not impermeable. History shows how easily human minds leap from data to stories. The canals of Mars, the first pulsar signals, dubbed LGM-1 for little green men. Each time, natural explanations prevailed, but each time, the speculation told us something about ourselves, about our hopes, our fears, our longing to not be alone. Atlas, in this sense, is a mirror. To most, it is a comet, silent, natural, unthreatening. To others, it is a thought experiment about worst cases, about the possibility that cosmic wanderers might sometimes carry intention as well as inertia. To all, it is a lesson. The universe sends us messages, sometimes in the form of signals, sometimes in the form of stones. Whether we see them as threats, as curiosities, or as invitations depends less on the object itself than on the stories we choose to tell about it. So, is 3i Atlas a threat? By every metric of physics, no. It will not strike us. It will not linger. It will not bend its trajectory in ways that defy Newton's laws. But in another sense, Atlas is threatening precisely because it demands that we ask questions we cannot easily answer. What else is out there? How much of what we call natural might mask the unexpected? What if the true danger lies not in rocks from the stars, but in the limits of our own imagination? As Atlas speeds through the solar system, trailing its faint cometary tail, it offers us a fleeting glimpse into galactic deep history. It carries chemical secrets from a world we may never see. It forces us to test our instruments, our theories, and our narratives, and when it departs, as it surely will, it leaves behind a legacy of wonder and unease, a reminder that the void is not empty, that the stars send gifts, and that every encounter, natural or not, reshapes our sense of who we are in the cosmos. Part 2: Speed, Size, Age. A quiet powerhouse. The numbers alone stagger the imagination. 3I Atlas races through the solar system at more than 130,000 miles per hour, roughly 150 times faster than a high-powered rifle bullet. Its hyperbolic excess velocity, 61 kilometers per second, represents the speed it retains even after accounting for the sun's pull, the enduring momentum of an object that has wandered the galaxy for untold eons. On paper, the math is straightforward. In practice, the implications push us toward questions that blur the line between astrophysics and speculation. Compared to its predecessors, Atlas is astonishing. Oumuamua, the first interstellar visitor, moved at 26 kilometers per second. 2I Borisov followed at 32 kilometers per second. Atlas streaks nearly twice as fast as either. Such velocity could be the result of violent ejection from its birth system, or the cumulative effect of gravitational slingshots across many encounters in its cosmic odyssey. But another possibility lingers at the edges of imagination. What if the steady increase in velocities across 3 consecutive interstellar objects is not mere coincidence, but signal, a trend hinting at something deliberate, beyond the reach of our instruments, nudging us to consider scenarios that verge on design? Determining Atlas's size is harder. The coma of gas and dust obscures its nucleus, forcing astronomers to infer dimensions indirectly. Current estimates range from just 0.3 kilometers to as large as 5 or 6 kilometers across, from the scale of 3 football fields to a small mountain. Most models lean toward the lower end, based on reflectivity and coma efficiency. But even a body a few hundred meters wide is formidable when crossing interstellar space. And here, too, uncertainty opens the door to speculation. Does the vagueness of our measurements conceal more than ignorance? Could ambiguity itself mask features we have not yet learned to interpret? Survival is the puzzle. How could such a modestly sized body endure the violence of ejection from its home system, then drift for millions or billions of years in the hostile medium between stars? Small objects are fragile. They are vulnerable to tidal disruption near giant planets, to shattering collisions with micrometeoroids, to erosion by cosmic rays. And yet Atlas persists, intact, defying statistical odds. Natural explanations abound. Perhaps its composition is unusually robust. Perhaps it has avoided encounters by luck. But if one were inclined to read intention into endurance, the possibilities become less comfortable. What if Atlas endures not because of chance, but because it was built to? Age only deepens the mystery. Orbital analysis suggests that Atlas originates in the Milky Way's thick disk, a population of ancient stars with orbits more chaotic than the orderly thin disk around us. If so, this object could be billions of years older than our solar system, forged when the galaxy itself was young. Within its icy interior might lie chemical records from an era when the universe was less than half its current age. A natural time capsule, yes, but also a reminder of just how alien its origin may be. For those willing to speculate, the antiquity of Atlas becomes a stage for unsettling thoughts. Could an object this old embody not only cosmic history, but cosmic intent? The approach angle reinforces its strangeness. Most local objects align broadly with the galaxy's rotation. Atlas does not. Its path cuts across that order, suggesting membership in a population that has never been tidied by galactic evolution. The astronomical explanation is clear, but once again the speculative shadow lengthens. If we dared to imagine intentional navigation, how different would its trajectory look from a random one? Despite its velocity and antiquity, Atlas poses no physical risk. Its hyperbolic path guarantees escape. It moves too fast for solar capture, and its closest approach remains measured in astronomical units, not kilometers. The worst case, in other words, is not collision. The worst case is revelation, the possibility that Atlas embodies meanings we are only beginning to glimpse. Observation itself is a challenge. At peak brightness the object is faint, around magnitude 11, requiring significant telescopes under perfect skies. Its closest approach to the Sun coincides with its disappearance into solar glare, a cosmic irony that denies us clarity just as the visitor becomes most active. The timing feels almost cruel, and yet limitation itself tempts speculation. What happens in the gaps, when our instruments are blinded? What truths might unfold unseen, when the data go dark? What emerges is a portrait of paradox. Atlas is at once ancient and fleeting, immense and elusive, natural and uncanny. It is a comet by every measurable standard, yet it stirs questions about survival, design, and purpose. The laws of physics describe its path precisely, allowing us to chart its location years in advance. But when we dare to ask what lies beyond orbital mechanics, the equations give way to unease. Perhaps the real danger Atlas carries is not impact, but implication. It reminds us that the cosmos operates on scales of time and speed that dwarf human intuition, and that even when an object poses no risk at all, it can still challenge our imagination with possibilities we are not yet prepared to confront. Part 3. Chemistry in the Quiet. COTU, Overdrive. When the James Webb Space Telescope turned its infrared eye toward 3I Atlas on the 6th of August 2025, the spectrum it returned was unlike anything astronomers had ever seen. Instead of the familiar dominance of water vapor, Webb detected a coma ruled almost entirely by carbon dioxide. The CO2 to water ratio was approximately 8:1, not just unusual, but unprecedented in the study of comets. For planetary scientists, this was a revelation. For those inclined to speculate, it was a provocation. What if this molecular signature pointed to processes, or even purposes, that stretched far beyond natural explanations? Ordinary comets follow a predictable chemical script. As they approach the Sun, water ice sublimates first, producing vapor plumes mingled with dust. Carbon monoxide appears next, then carbon dioxide, then a smattering of other volatiles. The exact ratios tell a story of formation, whether the comet was born near or far from its parent star, how it has aged, what radiation it has endured. But 3I Atlas tore up that script. It seemed to breathe CO2 in volumes that dwarfed water, a kind of chemical imbalance almost industrial in scale. If water comets whisper of icy birthplaces, Atlas shouted of origins we could not easily place within natural categories. The anomaly grew sharper when distance was considered. At the time of observation, Atlas was more than 3 astronomical units from the Sun, well beyond Mars. Most comets are quiet there, too cold for serious activity. Yet Atlas displayed a glowing coma stretching hundreds of thousands of kilometers, rich with carbon dioxide. Theories emerged quickly. Perhaps Atlas formed near its natal star's CO2 snowline, where such ice is condensed more readily. Perhaps cosmic ray bombardment had sealed away its water ice beneath a crust, leaving CO2 as the only escape. Perhaps ancient dust mantles insulated volatile layers in unexpected ways. These were plausible explanations. And yet, the more we reached for natural causes, the more some asked, what if this chemistry was not accident, but artifice? Webb's near-infrared spectrograph is precise enough to fingerprint individual molecules, recording the unique wavelengths of light emitted as sunlight excites a comet's gases. The observed ratio was among the most extreme ever captured. To cautious astronomers, this was simply a data point, evidence that our models of cometary diversity remain incomplete. To the speculative imagination, it was something else entirely. Could chemical signals themselves serve as carriers of information? Could volatile ratios be used the way humans use radio pulses, a form of message written in molecular language? There was precedent of a sort. Comet C, divided by 2016 R2, pan-stars, had startled researchers with unusual enrichments in carbon monoxide and nitrogen. That anomaly was explained as the outcome of rare formation conditions, but it proved that outliers exist. 3I Atlas, however, push the boundaries further. One comet with odd chemistry is a curiosity. 2, 3, or more could start to look like a pattern. And when patterns emerge, speculation inevitably follows. From a strictly scientific standpoint, Atlas offered a priceless glimpse of chemistry from beyond our solar system. Every interstellar visitor is a messenger from an alien stellar nursery. Each carries the imprint of physics and chemistry from environments we may never see directly. Even without invoking anything artificial, Atlas forced a recalibration of how wide the spectrum of cometary chemistry might be across the galaxy. But when scientists acknowledged its extreme antiquity, the likelihood that it originated in the Milky Way's thick disk, billions of years older than our solar system, the speculation deepened. Was it so unthinkable that ancient intelligences might encode information not in radio signals, but in the chemistry of objects flung between stars? The real test would come as Atlas approached the Sunday. If its chemistry changed with heating, revealing buried layers of water ice or hidden volatiles, then the CO2 dominance might be explained as a surface phenomenon. But if the ratio remained consistent, even as solar energy drilled deeper, then something stranger might be at play. Some scientists began preparing statistical frameworks to test whether emerging molecular patterns showed the fingerprints of deliberate encoding rather than random physics. Could repeated ratios or sequences act like binary strings? Could sublimation curves be read as intentional activation rather than passive heating? Whatever the outcome, Atlas underscored the limits of our models. If comets from other stars routinely display exotic chemistries, then planetary formation is far more diverse than we imagined. Our theories may be provincial, built too narrowly on the sample of one solar system, but if, after every attempt at natural explanation, anomalies remain, then we may be glimpsing processes beyond geology, beyond chemistry, processes that edge toward technology. Seen from a broader perspective, Atlas was less a threat than a challenge. It dared our instruments to reach deeper, our models to stretch wider, our imagination to admit possibilities we prefer to ignore. Its coma of carbon dioxide was not simply an exotic chemical imbalance. It was a quiet powerhouse, a signpost pointing toward conditions or intentions we do not yet fully understand. The lesson was twofold. First, humility. Our grasp of interstellar chemistry is fragile, and nature may be stranger than we assume. Second, vigilance. Sometimes anomalies are not just data points, but invitations. Atlas reminded us that when the universe writes its stories in molecules, the line between geology and message may be thinner than we think. Part 4. Worst Case Answered. Nearly 2,000 words into our investigation, the supposed worst-case scenario resolves into something refreshingly ordinary. No Hollywood catastrophe lurks on the horizon. No extinction-level impact bears down on Earth. No gravitational disruption threatens to sling our planet from its orbit. Instead, the verdict is precise, mathematical, and calming. Celestial mechanics assures us that 3I Atlas poses no physical danger. We can, at least in principle, rest easy. And yet, beyond the safety of these calculations, lies another landscape, not one of orbital risk, but of speculative possibility. What if the true worst-case scenarios for 3I Atlas are not about collision, but about meaning? What if the threat comes not from what this object could do to us, but from what it might reveal about us, our assumptions, and our place in the cosmos? The numbers bear repeating, because they are the anchor to which everything else must be tied. 3I Atlas will approach no closer than 1.8 astronomical units, roughly 270 million kilometers from Earth. That is twice the Earth-Mars minimum distance, and more than 50 times the separation between Earth and the Moon. Its perihelion on the 29th of October places it about 1.4 astronomical units from the Sun, between the orbits of Earth and Mars. Close enough for sunlight to ignite its ices, spectacular enough to bloom into a glowing CO2 coma, but far too distant to disturb planetary orbits or rain debris on Earth. These are not rough guesses. They are calculations refined by centuries of celestial mechanics, cross-checked with decades of near-Earth object tracking. Gravitational perturbations, relativistic effects, even solar radiation pressure are accounted for. When astronomers state that Atlas is harmless, they speak from a bedrock of confidence. And yet, one can ask, what if safety itself is the illusion? What if the absence of physical threat is precisely what allows subtler, stranger possibilities to emerge? Consider speed. Atlas hurtles inward at more than 130,000 miles per hour. That velocity guarantees freedom. It cannot be captured by the sun, cannot linger in our system. Within months it will be gone, vanishing back into interstellar night. But here the speculative shadows stir. What if such velocity is not only the product of ejection or gravitational chance, but of design? What if its timing, its arrival in this century, visible to our instruments, reflects purpose? A flyby that looks random could, to a more advanced intelligence, be as deliberate as an orbit. This is where communication and risk intersect. Agencies like NASA take care to separate scientific interest from threat assessment. They emphasize, correctly, that interstellar carries emotional weight out of proportion to actual danger. Our brains, evolved to flinch at approaching objects, struggle to reconcile instinct with orbital geometry. A cosmic wanderer stirs unease even when its path is harmless. But this focus on impact risk may blind us to another dimension. The risks that come, not from collision, but from recognition. What if the worst case is not destruction, but contact? NASA's public communication has been exemplary. Clear, jargon-free statements stress both the remarkable scientific significance and the complete absence of hazard. Journalists, too, have largely echoed this mature approach. The headlines highlight curiosity, not catastrophe. In context, this is the right framing. Oumuamua in 2017 and Borisov in 2019 posed no danger, and neither does Atlas. The pattern seems secure. Interstellar visitors are fascinating, but harmless. But speculation persists, because patterns invite interpretation. What if the arrival of 3 interstellar objects within a single decade is not random but representative? Could the galaxy be conducting, knowingly or not, a kind of census, a steady revelation of messengers whose meaning lies less in their trajectories than in their timing? What if harmlessness itself is the point? A way of slipping past our instinct for threat to confront us, instead, with questions of intelligence, of design, of whether we truly are alone? The data we possess form a reassuring foundation. We know Atlas's speed, trajectory, and orbital parameters. We know its coma is unusually rich in carbon dioxide. We know its likely antiquity, rooted in the thick disk of the Milky Way. Multiple telescopes, from Hubble to Webb to ground-based arrays, confirm these facts independently. The picture that emerges is one of a fast, ancient, chemically exotic but ultimately natural comet. Everything points in the same direction, and yet uncertainties remain. The nucleus may be as small as a few hundred meters, or as large as several kilometers. The reasons for CO2 dominance are still debated. Is it bulk composition, surface expression, or ancient radiation chemistry? Its precise stellar birthplace is unknown. Its journey through gravitational encounters cannot be reconstructed with certainty. None of these unknowns alters the risk assessment, but each opens cracks through which speculation seeps. Each becomes a platform for imagining scenarios that natural explanations cannot easily contain. This is how science and imagination diverge. Science confines itself to the measurable: trajectories, spectra, sizes, ratios. Imagination asks, what if? What if the very absence of artificial signals or maneuvers is itself the signature of something beyond us? What if intelligence advanced far enough could hide behind natural laws so seamlessly that only anomalies like Atlas's chemistry remain as hints. Every measurement so far points toward the same conclusion. Atlas is what it appears to be, a comet born under alien conditions, behaving in line with universal laws. That in itself is profound. Confirmation of universality, that the physics and chemistry we know apply equally to fragments from other stars, is one of the deepest discoveries possible. By that definition, the worst case is already disproved. There is no impact, no danger. The object comes in peace, whether by intention or inertia. But now we reach the threshold where fact ends and speculation begins. The domain where worst cases are not about bodies and orbits, but about meaning and implication. Here, possibilities multiply like mirrors facing one another. What if Atlas is not just a comet, but a kind of message? What if its chemistry encodes information? What if its timing is deliberate? These are not scientific conclusions. They are thought experiments, mental rehearsals for futures that may never come. The evidence, as it stands, is clear. 3I Atlas is almost certainly a natural comet, harmless in every measurable sense. Yet in its very harmlessness lies a different kind of danger, not to our survival, but to our certainty. For Atlas reminds us that the universe is stranger, older, and perhaps more intentional than we dare to admit, and in that reminder, speculation takes root. But let us consider, carefully and deliberately, what it would mean if the evidence we have gathered were incomplete, misleading, or simply interpreted too narrowly. The baseline is firm. NASA, the European Space Agency, and virtually every mainstream astronomical institution describe 3I Atlas as a natural cometary visitor. This is not bureaucratic inertia, nor scientific conservatism for its own sake. It is the conclusion that best fits the available data. Atlas exhibits every hallmark of a comet: predictable orbital mechanics, sublimating ices, and spectroscopic fingerprints consistent with frozen volatiles interacting with sunlight. Occam's razor, the principle that the simplest explanation is usually correct, strongly favors this natural interpretation. And yet science has a long memory of surprises. Some of the most revolutionary discoveries began with signals or objects that appeared, at first, to be ordinary. Pulsars were initially catalogued as inexplicable radio beacons, so regular that the Discovery team jokingly labeled them LGM, Little Green Men. Only later did they prove to be rapidly rotating neutron stars, lighthouses of collapsed matter. Fast radio bursts baffled astronomers for more than a decade, each burst lasting only milliseconds, their sources elusive. Eventually, careful observation revealed that some were produced by magnetars, highly magnetized remnants of dead stars phenomena, stranger than early speculation. The lesson is clear. Sometimes nature exceeds our imagination. Could 3I Atlas represent another chapter in this tradition? A case where the universe reveals itself to be stranger than first assumed. Speculation about artificial origins does not emerge in a vacuum. Harvard astrophysicist Avi Loeb, already known for his controversial interpretation of Oumuamua as possible technology, has raised similar questions about Atlas in interviews and blog posts. His position, always careful to note that it is opinion rather than established fact, is simple. We should not dismiss the possibility that some interstellar visitors are artificial. Even if unlikely, the mere consideration sharpens our thinking. What would convincing evidence of an artificial origin look like? Which observations would force us to abandon the comet hypothesis in favor of something engineered? These questions matter not because they are likely, but because they help us refine the boundary between rigorous skepticism and reflexive dismissal. If Atlas were artificial, what signs might betray it? Coherent radio emissions would be the most obvious. Natural objects radiate noise, but only technology produces narrowband, structured signals. A genuine artificial transmission would be unmistakable, ordered, repeating, mathematically intentional. Non-gravitational accelerations would be another clue. Natural comets often show subtle deviations, as jets of vapor act like thrusters. But if Atlas accelerated in ways inconsistent with sublimation, or in patterns disconnected from solar heating, that would hint at propulsion. Light curves, too, could reveal anomalies. Comets brighten as they near the Sun, with variations tied to rotation and surface heterogeneity. An artificial object might brighten or dim in ways that suggest controlled orientation or active systems. So far, none of these signatures have appeared. Radio observatories report only silence, broken by the expected hiss of natural outgassing. Atlas's orbit tracks celestial mechanics precisely, without unexplained deviations. Its brightness variations match what astronomers expect from rotating cometary nuclei shedding dust and gas. The chemical anomaly, its coma dominated by carbon dioxide, is striking, but not proof of artifice. Several natural processes could plausibly account for it: formation near a CO2 snowline, radiation processing over billions of years, or insulating dust mantles that release carbon dioxide preferentially. To leap from unusual chemistry to engineered construct requires evidence far stronger than we currently possess. Here the lessons of Oumuamua matter. That first interstellar visitor triggered waves of speculation because of its elongated shape and its subtle acceleration. But deeper analysis showed that outgassing of ordinary ices could explain the effect, even if the jets were invisible. Radio telescopes searched for transmissions and found none. The extraordinary hypothesis that it was a probe failed under scrutiny. The natural explanation held. The precedent is instructive: maintain openness to radical possibilities, but demand extraordinary evidence before accepting them. This is why careful communication matters. When journalists or commentators raise the possibility of artificial origin for Atlas, the claim must be labeled clearly as speculation, not fact. The distinction shapes public understanding, not only of this object but of the scientific process itself. Speculation has value, it keeps us imaginative, it prevents complacency, but it must be framed responsibly. Otherwise, fascination shades too quickly into fear, or science into sensationalism. Still, the exercise of considering artificial scenarios is more than entertainment. It forces us to define what separates natural from artificial phenomena. It encourages us to invent observational tests capable of falsifying the comet hypothesis. It reminds us that the universe has not yet yielded all its surprises, and that the line between known and unknown is porous. Future data will continue to probe these boundaries. As Atlas approaches perihelion, new spectra may reveal chemical profiles even stranger than those already observed. More precise astrometry could uncover minute deviations in trajectory, hinting at controlled motion. Long-term monitoring may reveal brightness variations inconsistent with passive behavior. If any of these occur, the natural comet hypothesis would be challenged. Until then, it remains the most consistent explanation, supported by physics, precedent, and observation. The burden of proof lies with those who propose the extraordinary. Natural explanations, though imperfect, align with what we know of planetary formation and interstellar debris. Artificial hypotheses, by contrast, demand evidence that natural processes cannot plausibly explain. The scientific method is indifferent to our hopes or fears. It demands rigor from all claims alike. And yet, none of this diminishes Atlas's importance. Even as a natural comet, it is extraordinary, a fragment of a stellar system we may never see, carrying chemistry from a time billions of years before our own sun was born. It is a messenger from galactic history, delivering to our doorstep information about environments utterly alien to us. That is wonder enough without invoking probes or intelligence. Indeed, some of astronomy's greatest breakthroughs arose from careful study of the seemingly ordinary. Pulsars, quasars, gamma-ray bursts, gravitational waves, each began as puzzling signals that revealed new physics. Whether Atlas ultimately proves exotic or mundane, it has already enriched our understanding of interstellar space and the diversity of objects that wander between the stars. Speculation will continue, as it should. Thought experiments about artificial origins serve as mental training, preparing us for the day when evidence may demand such a conclusion. But until then, the balance of probability leans heavily toward nature, not technology. The carbon dioxide coma, the hyperbolic trajectory, the predictable brightening near perihelion all align with a natural explanation. Still, in the quiet space between data points, imagination persists. Atlas reminds us that every discovery carries two stories, the one written in mathematics and spectra, and the one we tell ourselves in the shadows of possibility. For now, the mathematics dominate, but the speculation properly framed, clearly labeled, keeps us ready for the day when the shadows themselves might speak. Part 5. Worst case. Speculative scenario. A dark forest trigger. We now step fully into the realm of imagination, into the speculative shadows where evidence does not yet tread, but where possibility itself demands our attention. This is not science in the strict sense. It is thought experiment, an exploration of what might follow if our assumptions about 3I Atlas prove inadequate. The dark forest hypothesis provides the frame. Born from both science fiction and serious SETI discourse, the idea takes its name from Liu Cixin's celebrated novel, but represents a genuine philosophical concern. In a galaxy where civilizations arise and fall, survival may depend on silence. Any species that reveals itself risks predation from neighbors more advanced and more ruthless. In such a universe, caution is not paranoia but strategy. To remain hidden is to endure. To announce oneself is to invite annihilation. If we allow ourselves to imagine, and it must be stressed, this is imagination, that 3I Atlas is not a natural comet but a reconnaissance probe, the implications become staggering. Such a scenario would suggest that our solar system is already under survey by minds capable of disguising technology as ice and dust, minds able to build machines that survive billion-year journeys while masquerading perfectly as natural debris. The disguise itself would speak of sophistication far beyond our own. Consider what such engineering would require. A probe meant to pass as a comet must mimic every detail of cometary behavior. Spectroscopic fingerprints matching frozen volatiles, outgassing jets that vary with solar heating, brightness patterns consistent with rotation, surfaces that scatter light like natural ices. It would need genuine volatile material to maintain its deception as it swung past stars. At the same time, it would have to conceal sensors, communication systems, and energy supplies capable of surviving deep time. Power sources alone push the limits of imagination. Perhaps nuclear decay could trickle energy across millennia. Perhaps advanced fusion reactors could sip trace interstellar hydrogen. Or maybe such a machine would harvest energy from cosmic rays and magnetic fields, turning the emptiness of space itself into fuel. And what if the disguise began to slip? Imagine radio telescopes detecting bursts of structured transmission as Atlas arcs past the outer planets. Imagine precise astrometry revealing minute course corrections inconsistent with gas jets. Imagine chemical emissions displaying patterns too complex, too regular, to arise by chance. Each anomaly would raise the same question. What if this was never a comet at all? The scenario sharpens further with one speculative leap: deployment. What if, during perihelion, Atlas shed smaller fragments, not debris but daughters, probes of its own? One settles into orbit around Venus, another drifts toward Mars, others anchor themselves in the asteroid belt or at Earth-Moon Lagrange points. Suddenly our solar system would no longer feel empty. It would be threaded with sentinels of unknown origin and purpose. The immediate challenge would be political as much as scientific. Who speaks for Earth in such a crisis? The United Nations, the spacefaring powers, a consortium of scientists. The scramble for authority would be fierce. Humanity has struggled to achieve consensus on climate, trade, even public health. How would we respond to the revelation that a superior intelligence was already operating in our cosmic neighborhood? SETI debates would take on new urgency. For decades, the question has been whether to remain passive listeners or to broadcast our presence. Critics of active SETI, also called METI, messaging, extraterrestrial intelligence, argue that advertising ourselves could draw predators. Supporters counter that our radio leakage has already betrayed us, and that silence offers no real protection. But in this speculative scenario, choice itself would vanish. If Atlas were a probe, then the decision to reveal or conceal would already be moot. Our broadcasts, our satellites, our internet backbones leaking radio noise, all would be catalogued. Even our debates about how to respond would become data, analyzed for insight into human psychology. Silence might read as fear, caution as wisdom, communication as aggression or curiosity. Every move would be observed. The crisis in communication would be profound. How do you inform the global public that alien surveillance systems may be operating overhead? How do you balance transparency with stability? History shows how quickly misinformation can overwhelm truth in times of uncertainty. The suggestion alone would ignite conspiracy theories, false flag accusations, and denials. Distinguishing rigorous science from baseless panic would become an existential necessity. The technological implications are equally staggering. If Atlas possessed capabilities beyond current physics, propulsion without fuel, power without decay, materials immune to erosion, the mere observation of such systems could transform human science. The data might leapfrog us centuries ahead, offering solutions to energy crises, propulsion bottlenecks, even environmental collapse. But such gifts, if they were gifts, would arrive from an intelligence that may not exist anymore. For here lies perhaps the most haunting possibility. Atlas may have traveled for billions of years. If it is artificial, it could be the artifact of a civilization long extinct. Its builders might have vanished before our sun was born. What remains is machinery, autonomous systems carrying out programs with mechanical fidelity long after their masters were gone. Humanity would then face not an encounter with living minds, but with the ghosts of intelligence machines executing missions without context, relics of a vanished era. This is the chilling heart of the dark forest scenario. If Atlas is a probe, then we are already discovered. If it is a ghost probe, then discovery may not even matter. The hunter may have died before the prey emerged. But the principle remains. Survival in a universe of unknowns may hinge not on what we know, but on what others already know of us. And yet, this must be repeated, none of this speculation is supported by current evidence. Every observation to date confirms the natural comet hypothesis. Atlas behaves exactly as theory predicts. It brightens as it nears the sun, it sheds volatiles, it follows a hyperbolic orbit. Its carbon dioxide anomaly, while unusual, falls within natural variation. Its trajectory is clean. No transmissions, no course corrections, no daughters have been detected. The comet hypothesis remains robust. The value of exploring these speculative scenarios lies not in their likelihood, but in their capacity to sharpen our thinking. They force us to articulate what evidence would be needed to change our minds, what thresholds would force science to declare, "This is not natural." They remind us that the universe has surprised us before and will again, and they prepare us mentally, philosophically for the possibility that one day an interstellar visitor may not be what it seems. For now, 3I Atlas remains exactly what the data show: a natural comet, ancient, fast, chemically unusual, but within the grasp of science. The dark forest scenario is an imaginative mirror, reflecting our fears more than the object itself. Whether that mirror reveals paranoia or preparation may depend less on Atlas and more on us. Part 6. Great Filter Alarms. The Great Filter is one of the most unsettling ideas to emerge from our attempts to understand the silence of the universe. If life should be common, if stars and planets abound in their billions, then why do we see no evidence of other civilizations? This puzzle, first voiced by Enrico Fermi in the 1950 seconds, has become a central question in astrobiology and SETI. Somewhere, it seems, there must be a barrier, a filter that prevents life from arising, or surviving, or enduring long enough to spread among the stars. In the context of 3I Atlas, even as we remind ourselves that current evidence overwhelmingly supports a natural cometary origin, speculation forces us to confront the possibility that this ancient wanderer could be a messenger of failure. If Atlas were artificial, a probe, an artifact, then the question would immediately shift from what it is to what became of its makers. Did they endure, or did they fall victim to their own great filter? The hypothesis itself admits many possible forms. The filter might be early, at the boundary between chemistry and biology, where the jump to self-replicating systems proves improbably rare. Or it might come later, when civilizations achieve technology powerful enough to destroy themselves faster than they can learn to wield it wisely. Nuclear weapons, climate collapse, engineered pandemics, uncontrolled artificial intelligence, each represents a modern echo of the dilemma. Technical mastery opens doors, but wisdom determines whether stepping through them leads to flourishing or extinction. If 3I Atlas were engineered, its apparent antiquity becomes chilling. Estimates of its trajectory suggest origins in the thick disk of the Milky Way, a stellar population billions of years older than our Sunday. To imagine it as artificial is to imagine technology built long before Earth's continents assumed their present shape, perhaps even before the solar system itself was born. That raises an immediate paradox. Could the civilization that launched it possibly still exist? Or are we encountering only their echo, their residue, their ghost machines crossing deep time? The timescales stagger the imagination. Human civilization stretches 10,000 years if we include agriculture, 5,000 if we count recorded history, scarcely centuries if we mean spaceflight. 3I Atlas, if artificial, would represent engineering sustained for millions of times longer. The pyramids and radioactive isotopes we call permanent are dust compared to what such technology implies. To function across billions of years, a probe would require materials harder than diamond, power systems more stable than stars, software that repairs itself indefinitely. It would mean mastery of durability at scales we can hardly conceive. Such achievements would also testify to the extraordinary capability of its builders. Any society able to launch probes across interstellar gulfs and keep them active across geological epochs must have solved problems we have only begun to contemplate. They would have mastered atomic-level manufacturing, cosmic-scale energy harvesting, perhaps even adaptive intelligences that evolve with time. Such skill should, one might think, protect them against collapse. And yet, if Atlas is all we see, then perhaps even they could not escape their filter. The possibilities are sobering. Perhaps they consumed resources too quickly, exhausting energy and matter at scales we cannot fathom. Perhaps they encountered others like themselves, not friends, but predators, and the result was mutual destruction. Perhaps the very tools that let them build probes became their undoing, weapons more devastating than any defense, environmental ruin on interstellar scales, social fractures that technology could not heal. The story of humanity suggests how plausible this path might be. Invention racing ahead of wisdom, capacity exceeding restraint. Another possibility is subtler. The filter may not be annihilation but transformation. Civilizations might advance beyond our recognition, merging with technology until distinction disappears, uploading consciousness into quantum substrates, or ascending into higher dimensional states. Such beings would not vanish but would cease to be visible to us. To emerging species like ours, their silence would be indistinguishable from absence. The cosmic perspective makes this vertiginous. The Milky Way holds roughly 400 billion stars. Many formed billions of years before the Sunday. If even a tiny fraction birthed civilizations, then by now the galaxy should be full of their works. The fact that it is not, or at least not obviously, is the great silence. If Atlas were artificial, it might serve as rare evidence that others once lived, thought, and built, but that their voices have long since gone quiet. SETI practice reflects this unease. Most projects emphasize listening, not transmitting, wary of shouting into a dark forest we do not understand. The discovery of artificial signatures in Atlas would overturn that caution instantly. We would no longer be listening for hypothetical signals. We would be confronting physical proof that someone had crossed the filter, at least long enough to send their artifacts outward. The question would then be what happened afterward and whether their fate awaits us. It is important to stress, again, that current observations do not justify this leap. Every spectrum, every image, every orbital calculation supports the comet hypothesis. Speculation about engineered probes and failed civilizations remains just that, speculation. But even as thought experiment, the scenario forces reflection. If advanced civilizations fall victim to filters they cannot escape, then our own trajectory must be examined with sharper eyes. The Great Filter serves both as warning and as mirror. It warns us that technology alone is not enough, that every new capability carries new risks. It reminds us that survival across cosmic time is not guaranteed, that wisdom, restraint, and adaptability are as important as innovation. But it also reflects our responsibility. If others fell, then perhaps we might learn from their absence. If others transcended, then perhaps we might aspire to join them. The choice is not predetermined. In our speculative narrative, Atlas becomes more than a comet. It is a time capsule, a relic of intelligence that may have solved interstellar engineering only to fail at survival. It drifts on, mission parameters intact, long after the hands that built it are dust. If that were true, then humanity would find itself in a position of inheritance. We would be heirs not just to Earth's history but to galactic history, tasked with learning from both achievements and failures that predate us by billions of years. But this is philosophy, not physics. The real Atlas continues to behave like a comet, sublimating, brightening, tracing its hyperbolic arc. The Great Filter remains a hypothesis, untested and unproven. The danger lies not in Atlas itself but in what we project onto it. The cosmos has proven strange enough without requiring alien machines to deepen our wonder. Quantum mechanics, black holes, dark matter, and the web of galaxies already stretch the limits of comprehension. Whether or not intelligence hides among the stars, the universe offers mysteries enough, and yet the thought remains. If Atlas is natural, then it is a gift of knowledge. If it is artificial, then it is a warning. Either way, it forces us to ask what barriers lie before us, and whether we will have the foresight to navigate them. In that sense, the Great Filter is less about them than about us. The true alarm is not that others may have failed, but that we might repeat their fate if we do not learn. Part 7. Fermi Whisper. Where is everybody? The question lingers like an echo in the night sky. Where is everybody? Enrico Fermi's casual lunchtime remark in 1950 has grown into one of the deepest puzzles in modern thought. If the galaxy contains hundreds of billions of stars, if planets abound, if life is not unique to Earth, then why do we find ourselves alone? The Fermi paradox haunts every astronomical discovery, every search for extraterrestrial intelligence, every moment when we peer into the dark and hear only silence. The paradox sharpens when we consider interstellar objects such as 3I Atlas. Each visitor from beyond the solar system is a physical sample of another stellar environment, a fragment of galactic history delivered to our doorstep. In principle, such wanderers could someday betray unmistakable traces of technology, engineered alloys, artificial isotopes, structured geometries that natural forces could never produce. And yet, to date, every confirmed interstellar traveler, Oumuamua in 2017, Borisov in 2019, Atlas in 2025 has appeared thoroughly natural. The silence persists, not only in radio searches, but in chemistry, structure, and motion. What if this absence is itself a message? Perhaps truly advanced civilizations prefer what we might call silent emissaries. If they dispatch probes at all, these machines are camouflaged, designed to be indistinguishable from natural debris. The more sophisticated the technology, the less it looks like technology at all. From this perspective, invisibility is not failure but design. Our instruments, tuned to recognize obvious artifice, may be missing subtler signatures altogether. But what would those signatures be? What could separate the natural from the artificial, if artifice is hidden so well? The most obvious candidate has always been narrowband radio emissions. Nature produces radio noise across wide frequency bands, the crackle of lightning, the roar of pulsars, the hiss of plasma. Technology, by contrast, tends to concentrate power in narrow spectral lines, signals that stand out against the cosmic background. For decades, SETI has listened for precisely such beacons, reasoning that any civilization capable of interstellar communication would use electromagnetic signals. Yet 3I Atlas has remained radio silent. Its emissions match only what we expect from solar wind interacting with cometary gases. No coherent patterns, no modulations, no whispers of intelligence. Silence aligns perfectly with the comet hypothesis, though it cannot rule out concealment. Thermal profiles offer another diagnostic. Natural objects achieve equilibrium with their environment. They absorb sunlight, radiate in the infrared, and maintain surface temperatures predictable from their composition and distance from the sunday. Artificial systems might deviate, betraying hidden power sources or active thermal regulation. An internal reactor would produce heat inconsistent with passive physics. A radiator panel might disperse energy in unnatural patterns. Infrared observations of Atlas, however, show nothing of the sort. Its temperature rises exactly as the inverse square law predicts, its surface distribution shaped by random topography rather than engineered control. Again, nothing out of place. Controlled maneuvers would be the most definitive telltale. Natural comets do drift, nudged by jets of sublimating ice, but the thrust is weak, chaotic, and directly correlated with coma brightness. Artificial propulsion would look different. Steady course corrections, intentional velocity changes, trajectories that suggest objectives rather than randomness. Precise astrometry could, in theory, reveal such intent. Yet Atlas glides smoothly along its hyperbolic arc, perturbed only by forces we understand: gravity, radiation pressure, and outgassing. If there is a hidden engine, it is either inactive or invisible to current methods. The natural explanation remains not only sufficient, but expected. Simulations of planetary system formation predict exactly this. Countless planetesimals flung into interstellar exile by giant planets during their chaotic youth. These icy shards wander for billions of years, some eventually crossing other stellar neighborhoods. The galaxy should be filled with them, and indeed, the trickle of detections may be the leading edge of a flood. The Vera Rubin Observatory, coming online later this decade, is expected to detect interstellar objects by the dozens each year, transforming them from rare curiosities into routine discoveries. This statistical framework offers one answer to Fermi's whisper. If natural wanderers outnumber artificial probes by millions to one, then of course all three of our first detections have been natural. The artificial may still exist, but drowned in a sea of debris. Detecting them would be like finding a single engineered needle in a haystack of natural hay that stretches across the galaxy. Atlas's unusual chemistry adds nuance to this picture. Its coma, dominated by carbon dioxide, seemed at first extraordinary. But as our sample of interstellar objects grows, we may find such diversity is normal. Different stars, disks, and environments produce different chemical fingerprints. What once seemed anomalous may soon reveal itself as ordinary variation. Diversity is not necessarily design, and yet the paradox persists. If civilizations exist, why do we not see them? If they build probes, why can we not recognize them? The possibilities split in unsettling directions. Perhaps we are alone, intelligent life is vanishingly rare, and we are the outlier. Perhaps others exist but stay silent, hiding in the cosmic forest for fear of predators. Or perhaps they are here, their machines passing through our skies, perfectly disguised as comets and asteroids. Each resolution to the paradox carries implications. If we are alone, our responsibility is immense. The survival of intelligence itself rests on us. If others hide, then the galaxy is less friendly than we hope, and caution is wisdom. If they are here but indistinguishable, then our tools, not their presence, are the limitation. Each scenario tells us as much about ourselves as about the stars. For now, the evidence remains clear. 3I Atlas behaves like a comet. Its silence, its thermal balance, its trajectory, all confirm the natural hypothesis. And yet, in that very silence, Fermi's question grows louder. Where is everybody? Perhaps the answer lies not in dramatic signals or obvious probes, but in whispers hidden within the ordinary. Perhaps the universe is filled not with absence, but with subtlety. And perhaps, as our instruments improve and our sample size grows, we will begin to hear those whispers in the chemistry of comets, the geometry of orbits, the patterns of anomalies we once dismissed. Until then, every interstellar visitor is both a discovery and a reminder. Discovery, because each expands our understanding of galactic processes. Reminder, because each arrives silent, leaving us to wonder if the true message is not what we find, but what we fail to see. Survey bias complicates everything we think we know about interstellar objects. Our telescopes do not see the sky evenly. Ground-based instruments are constrained by weather, atmosphere, and daylight. Space telescopes, though free of clouds, have their own blind spots and limited fields of view. Detection is not uniform. It is sculpted by geometry, brightness, thresholds, and the biases of our observing strategies. The 3 confirmed interstellar visitors, Oumuamua, Borisov, and Atlas, may represent only the most visible tip of a much stranger iceberg. This is not unprecedented. When the first exoplanets were discovered in the 1990 seconds, nearly all were hot Jupiters, giant planets orbiting extremely close to their stars. For a time, astronomers wondered whether our solar system was the anomaly, but the truth was simpler. Our early instruments were most sensitive to large planets tugging on their stars with rapid, obvious cycles. Only with improved methods did we reveal the true diversity of planetary systems. The same may hold for interstellar objects. The ones we've seen may not represent the population as a whole. Atlas itself illustrates the point. Its arrival from the southern skies surprised some researchers who expected most interstellar debris to follow the galaxy's overall rotation. The unexpected trajectory suggests either that our models of galactic dynamics remain incomplete, or that gravitational scatterings can mask original motion. A single close pass by a giant planet, billions of years ago, could send an object into a course that bears no trace of its birthplace. Each visitor is both a clue and a complication. Future tools promise clarity. The Rubin Observatory's Legacy Survey of Space and Time, LSST, will transform the hunt. Operating for a decade, it will scan the entire southern sky every few nights, generating an avalanche of data. Astronomers expect it to detect hundreds of interstellar objects, enough to build statistical samples that can test theories of origin, composition, and trajectory. Space-based infrared telescopes will complement the optical data, measuring thermal emissions, mapping surface properties, and characterizing ices with precision beyond today's reach. With larger datasets, we will either confirm the predictions of planetary formation theory that interstellar objects are natural debris scattered in youth, or encounter anomalies that demand more exotic explanations. And if artificial probes exist among the wanderers, large numbers and improved instruments may finally expose them. Patterns invisible in single examples might emerge across dozens. Subtle deviations from natural chemistry or motion, repeated again and again, could become statistically undeniable. The haystack may remain vast, but more needles may eventually shine through. The philosophical weight of continued silence should not be underestimated. Each new natural object strengthens the null hypothesis that intelligence capable of interstellar engineering either does not exist, remains beyond our detection, or deliberately conceals itself. Each cometary visitor deepens the impression of cosmic loneliness. But absence of evidence is not evidence of absence. Our surveys remain young, our capabilities narrow, our samples tiny. The universe may yet surprise us. And so, imagination wanders further than evidence. If Atlas were more than comet, what else might it be? One speculative scenario drifts toward the idea of microseeds. Imagine that Atlas is not merely a disguised probe, but a delivery system. Embedded within its icy matrix are microscopic devices, nanotechnological spores, or perhaps even engineered biological entities. Dormant, quiescent, patient, they wait for a trigger. This concept stretches existing science, but does not emerge from nowhere. The panspermia hypothesis has long proposed that life may spread between worlds on comets and asteroids. Hardy microbes might, in principle, survive radiation, vacuum, and time, seeding new biospheres when they find hospitable soil. Though unproven and controversial, the idea at least illustrates nature's capacity for persistence. The microseed scenario takes the thought further. Instead of passive microbes, imagine engineered constructs, machines or hybrid organisms designed to endure deep space for billions of years, activating only when specific conditions are met. What triggers might awaken them? Perhaps the electromagnetic fingerprints of technology, radio transmissions, power grids, radar pings, perhaps atmospheric chemistry, carbon dioxide levels rising with industrialization, or nitrogen oxides from engines. Perhaps simple stellar cues, activation when approaching stars of certain spectral types, when radiation intensity crosses a defined threshold. Each possibility implies intent, a design philosophy aimed not at blind dispersal, but at strategic timing. The engineering challenges are staggering. Devices must endure constant cosmic radiation, micrometeoroid impacts, and temperature swings from near absolute zero to hundreds of degrees. They must protect data across geological timescales, resisting entropy that degrades every known medium. They must harvest energy from environments that offer almost none. They must be small, countless, and redundant, so that even if most fail, a few succeed. To us, such demands border on impossible. To an intelligence millions or billions of years ahead, they might represent only prudent design. The strategic implications would be profound. A single object like Atlas could carry billions of microseeds, dispersed silently into planetary systems. Invasion would not be a cinematic arrival of ships and armies. It would be subtle, patient, invisible until activation. A civilization might wake to discover that the seeds had already spread, already observed, already prepared. The timeline could be vast. Activation might not occur until centuries or millennia after Atlas's passage. Perhaps the seeds are programmed to wait until humanity reaches certain thresholds: interstellar travel, nuclear-scale energy, planetary-scale networks. The delay would serve a purpose: allow reconnaissance, ensure that the seeds awaken when civilization is mature enough to be useful or dangerous enough to warrant preemptive control. It would also provide plausible deniability. By the time of activation, the connection to the original comet would be forgotten, dismissed as coincidence. And yet, the harsh realities of physics push back. Space is merciless. Radiation destroys polymers, metals corrode under micrometeoroid bombardment, electronics degrade without constant repair. Even the most robust biological spores have limits measured in millions of years, not billions. The odds of any complex system surviving intact across galactic timescales are vanishingly small. Here, skepticism must be firm. Nature is crueler than imagination, but imagination serves a purpose. The microseed scenario dramatizes our anxieties about vulnerability and surveillance. It reminds us that intelligence, if it exists elsewhere, may not resemble our expectations. It may prefer subtlety over spectacle, patience over proclamation. And it highlights the thin line between scientific mystery and speculative story. Both begin in the same silence and diverge in how we interpret it. In the end, 3I Atlas remains what the data say it is: a natural comet, strange but comprehensible, one more fragment of the galaxy's restless debris. The microseeds are narrative, not evidence. They belong to thought experiments rather than telescopes. Yet, the act of imagining them matters. It forces us to sharpen our methods, clarify what counts as evidence, and prepare our minds for futures where the improbable might become the real. The universe has never lacked for wonder. Quantum mechanics, black holes, dark energy, cosmic inflation, all have proven reality to be stranger than we dared assume. Whether or not Atlas carries hidden seeds, it carries something equally precious: the reminder that exploration is not only about what we observe, but about how we interpret the silences between the data points. Cosmic radiation alone presents an unforgiving barrier. Over million-year timescales, high-energy particles steadily shred molecular bonds, breaking apart complex structures atom by atom. Stretch that exposure across the billion-year journey suggested by 3I Atlas's apparent antiquity, and the challenge becomes insurmountable. Even the most radiation-resistant organisms known on Earth, tardigrades, bacterial spores, extremophiles that thrive in nuclear reactors, would succumb long before such a voyage reached its midpoint. If Atlas carried microscopic hitchhikers, they would be ghosts long before encountering our solar system. Outgassing makes the scenario harsher still. The very process that gives comets their beauty, sublimating ices erupting into space, dragging dust in luminous tails, would be catastrophic for any embedded microstructures. Every perihelion passage would unleash violent venting, scattering particles indiscriminately across millions of kilometers. Delicate devices or engineered spores would be torn apart, pulverized by gas jets, or dispersed into interstellar emptiness. Even if Atlas began its journey loaded with billions of microseeds, each cycle near a star would dilute their numbers further, scattering them across cosmic gulfs until only a vanishing fraction remained. Dilution continues at every stage. Suppose by some miracle a handful of microscopic seeds survived outgassing intact. They would still need to cross the immense distance separating Atlas's trajectory from Earth. At closest approach, Atlas will pass 1.8 astronomical units away, 270 million kilometers, roughly twice the minimum Earth-Mars distance. That gulf alone makes direct transfer implausible. The tiny survivors would then need to plunge through Earth's atmosphere, navigate its winds, and accumulate in sufficient concentration to matter. The odds stack so steeply against success that engineering such a mechanism seems profoundly inefficient. Current planetary protection protocols illustrate how we might respond to hypothetical contamination events. Space agencies already treat the possibility of cross-world transfer seriously. Missions returning samples from Mars, asteroids, or comets undergo strict containment procedures. Returned materials are quarantined in specialized biosafety facilities, analyzed for biological or chemical hazards, and studied with extreme caution. But these safeguards presume intentional sample return with controlled delivery to laboratories on Earth. They do not apply to passive dispersal of microscopic material drifting across interplanetary space. In that scenario, the monitoring problem becomes absurdly difficult. How would we even begin to search? Microscopic devices, or dormant organisms designed to survive for centuries, would be indistinguishable from ordinary microbes, dust grains, or terrestrial contaminants. No radar system, no optical survey, could reliably detect particles measured in micrometers scattered across the solar system. The challenge is equivalent to searching for a needle not in a haystack, but in a haystack spread across the size of Earth's orbit. Even if such seeds existed, the chances of us recognizing them are close to zero. And here lies the central weakness of the silent invasion scenario. It violates fundamental principles of efficiency. Engineering is about leverage, achieving goals with minimal complexity and maximum reliability. Any civilization capable of designing billion-year delivery systems would presumably command technologies far more direct. Why scatter microscopic spores across light years when one could transmit information at the speed of light via radio or dispatch autonomous craft capable of course correction and direct observation? Why rely on a strategy so wasteful, so vulnerable to attrition, when alternatives are simpler and more effective? The speculative microseed hypothesis therefore serves best as allegory. It illustrates how imagination can outrun physical plausibility when confronted with cosmic mystery. The same sense of wonder that fuels science can also generate anxieties untethered from evidence. The danger is not imagination itself. Imagination is necessary, but mistaking speculation for likelihood. Our responsibility is to draw bright lines between what is possible, what is plausible, and what is probable. For documentaries or public discussions, the need for disclaimers becomes crucial. Audiences must know when they are hearing established science and when they are venturing into speculative territory. Clear labels guard against confusion. They help maintain trust in science as a method grounded in evidence, even as they allow room for creative exploration of possibilities. The counter-narrative remains powerful in its simplicity. The most straightforward explanation for Atlas's behavior is that it is exactly what it appears to be: a comet. Its dust behaves like comet dust. Its spectrum matches sublimating ices. Its thermal evolution follows the inverse square law of solar heating. Its orbit traces the clean hyperbola of a body unbound to the sunday. None of these require exotic add-ons or hidden mechanisms. And yet, there is value in thought experiments that stretch beyond probability. They reveal much about ourselves. Our tendency to imagine invasions, seeds, or probes disguised as comets reflects both creativity and unease. We live in a universe that dwarfs us, and our stories of hidden threats and ancient machines echo our anxieties about survival, identity, and significance. By projecting these fears onto interstellar visitors, we dramatize our deepest uncertainties about intelligence in the cosmos. The real 3I Atlas is already remarkable without embellishment. It is a fragment of another star's story, a shard of chemistry forged in alien conditions, an emissary from the galaxy's restless tides. It offers us a fleeting chance to study matter untouched by the sun's formative environment. For astronomers, that is miracle enough. As we near the end of this speculative arc, reflection becomes necessary. Why do we push these scenarios to their limits? Because in doing so, we sharpen our appreciation for the boundary between fact and imagination. We learn to respect evidence while acknowledging uncertainty. We recognize that the cosmos does not need invasion scenarios to be wondrous. Its natural processes, supernovae, pulsars, black holes, galaxies spinning like wheels of fire, already challenge human imagination more profoundly than most fiction. The universe, in short, has never required embellishment to inspire awe. It is strange enough, vast enough, terrifying and beautiful enough on its own. Atlas reminds us of this truth. Whether natural wanderer or imagined Trojan horse, it reflects the deeper lesson. We confront the unknown not only with our instruments, but with our stories. The key is remembering which is which. Part 8. If 3I Atlas were a visitor, how would we respond? If 3I Atlas were more than a comet, how would humanity respond? The answer begins with what has already unfolded, a demonstration of global scientific collaboration at its best. Within hours of the 1st of July 2025, discovery by the Atlas survey in Chile, telescopes across the world shifted their gaze toward the faint speck. A carefully choreographed dance of institutions and individuals took shape. The response revealed how astronomy in the 21st century functions not as isolated efforts, but as an international network united by curiosity. The first steps followed long-established asteroid and comet protocols. The Minor Planet Center at Harvard's Smithsonian Astrophysical Observatory, acting as the clearinghouse, collected astrometric data from observatories worldwide. Each new measurement refined Atlas's orbital solution, confirming its hyperbolic trajectory. The European Space Agency's Space Situational Awareness Program contributed additional tracking, while NASA's Planetary Defense Coordination Office assessed impact probabilities. That calculation was swift and decisive. Atlas posed no threat to Earth, but its interstellar origin elevated the response far beyond routine. The Hubble Space Telescope received Target of Opportunity status, redirecting scheduled observations to capture imagery of the visitor. The James Webb Space Telescope soon followed, dedicating precious hours to study the object's peculiar carbon dioxide-dominated coma. Ground-based facilities from Mauna Kea to the Atacama Desert provided complementary coverage across wavelengths, while amateurs worldwide attempted their own glimpses through backyard telescopes. The entire enterprise unfolded transparently. NASA's website published frequent updates, written with both technical detail and public accessibility. The European Space Agency did the same, emphasizing international collaboration. Even popular magazines like Sky and Telescope combined scientific coverage with observing tips. This openness reflects how modern astronomy differs from its past. In earlier centuries, discoveries might languish in notebooks or private correspondence for months before dissemination. Today, discoveries are announced globally within hours. The International Astronomical Union's Central Bureau for Astronomical Telegrams, despite its antiquated name, distributes alerts instantly. Atlas's discovery was no exception. A networked response spanning continents emerged almost overnight. But what if the story had gone differently? What if subsequent observations had uncovered anomalies irreconcilable with natural explanations? Coherent radio signals, controlled trajectory adjustments, or the deployment of secondary craft? How would our institutions' scientific, political, economic scale up to meet the enormity of such a revelation? Existing frameworks provide hints. The International Astronomical Union demands extraordinary claims be confirmed by independent observatories before acceptance. The SETI Institute has long debated protocols for potential contact, emphasizing transparency, information sharing, and international cooperation. Space agencies maintain planetary protection guidelines to prevent biological contamination between Earth and other worlds. Yet none of these frameworks was built to address the active presence of non-human technology operating within our solar system. Jurisdictional questions would surface instantly. Who speaks for Earth? The United Nations? A coalition of spacefaring nations? The scientific community? The answer would not come easily. Rivalries that complicate climate agreements or trade negotiations pale compared to the stakes of first contact. Scientific curiosity might clash with national security. Some nations might see opportunity, others threat. The political dimensions are staggering. Any confirmation of alien technology would become a matter of national security for every major power. Militaries accustomed to viewing space as a domain of satellites and surveillance would suddenly face the reality of intelligence far superior to their own. The balance between openness and secrecy could shift overnight. Where astronomy has long thrived on transparency, political pressure might demand classification and restricted access. Technical challenges would prove equally daunting. Atlas, like all interstellar visitors, moves fast, too fast for interception with current spacecraft. Reaching it physically would take years we do not have. Our only plausible channel would be radio transmission, gambling on communication protocols we do not yet understand. The limits of our capabilities would be laid bare. Despite decades of robotic exploration, humanity remains confined to its own celestial neighborhood. Interstellar visitors pass quickly, leaving us with observation rather than engagement. Public communication would represent one of the greatest challenges. How do you tell 8 billion people that alien technology has been detected in the solar system? Past experiences offer cautionary lessons. The 1977 Wow! Signal sparked global headlines but could not be repeated or verified. Oumuamua's anomalies inspired speculation about probes before careful analysis restored confidence in natural explanations. Scientists have learned to tread carefully, distinguishing between intriguing data and definitive proof. But even with care, the modern media environment, with its 24-hour cycles and amplification of rumor, could overwhelm sober analysis. Social media platforms would be flooded with conspiracy theories, hoaxes, and speculative panic. The line between legitimate updates and misinformation would blur almost instantly. The economic implications would be profound. Markets thrive on certainty. Confirmed alien intelligence would replace certainty with volatility. Energy companies, aerospace firms, and defense industries might surge or collapse, depending on how alien technology was interpreted. Investors would speculate wildly on the value of new physics, new materials, or new energy sources. Financial systems could tremble, not from physical threat, but from human perception of opportunity and danger. Education and philosophy would feel the shockwaves as well. Curricula would need rewriting. Theological frameworks would confront new questions. How does faith adapt to confirmed non-human intelligence? Anthropologists, political scientists, and ethicists would suddenly find themselves at the center of a global conversation. Universities would need to pivot from studying human societies in isolation to situating humanity within a galactic context. The timeline adds urgency. Atlas, like all interstellar visitors, does not wait for our deliberations. Its hyperbolic trajectory guarantees a brief window of observability. Decisions, whether about communication, classification, or research priorities, would need to be made in months, not decades. The compressed timeframe would test institutional agility to the limit. Yet the real-world response to Atlas demonstrates resilience. Within weeks, astronomers had confirmed its interstellar nature, coordinated global observations, and initiated detailed analysis. This efficiency suggests that humanity already possesses some of the organizational foundations needed for extraordinary discoveries. Theoretical frameworks, SETI protocols, planetary protection measures, legal scholarship on space governance provide additional scaffolding. Imperfect though they may be, they are beginnings. Most importantly, the actual response to Atlas has emphasized openness, curiosity, and cooperation. Data are shared, discoveries publicized, findings scrutinized across borders. In this lies hope, for while we cannot know how humanity would react to true contact, the Atlas case shows we are capable of meeting the unknown with both rigor and humility. The story of 3i Atlas, then, is more than cometary science. It is a case study in how civilization approaches mystery. It reveals our strengths: rapid coordination, international networks, commitment to evidence. It also exposes our fragility: political divisions, economic volatility, vulnerability to misinformation. Whether Atlas is natural or hypothetically artificial, the manner of our response may matter as much as the object itself. Perhaps this is the lesson worth carrying forward. The universe will continue to send enigmas. Some may be comets, others something stranger. Our task is to meet them with clarity, distinguishing what we observe from what we imagine, what we know from what we fear. If we can do that, then whatever visitors the cosmos sends next, humanity may yet be ready to answer. Part 9. Containment or curiosity. Containment or curiosity? Few questions strike so directly at the heart of human exploration. From the first ocean crossings to summits scaled at the edge of death, our species has always balanced the thirst for knowledge against the instinct for safety. The same tension extends into space. Should we shield ourselves from the unknown, or open our instruments and imaginations to whatever the cosmos may reveal? In the case of 3I Atlas, the scale tips decisively toward curiosity. Its trajectory and properties eliminate almost every conceivable containment scenario, while maximizing opportunities for shared discovery. Planetary protection doctrine offers the framework. Built over decades of exploration, it sets procedures for managing contamination risks in both directions, protecting Earth from alien microorganisms and protecting other worlds from terrestrial life. These principles have guided sample return missions, sterilization of spacecraft, and the cautious handling of Mars regolith or Europa-bound probes. Yet these protocols assume proximity direct landings, returned containers, physical contact. They were not designed for a comet hurtling past at nearly twice Earth-Mars distance, a body displaying no evidence of biological activity. The architecture of planetary protection rests on proportional response. With Perseverance's Mars samples, the stakes demanded extraordinary precautions. With 3I Atlas, the physical distance 1.8 astronomical units, some 270 million kilometers, renders physical containment irrelevant. That distance has enabled something rare in modern science: truly open observation. Data from Hubble, Webb, and ground-based telescopes flow into public archives almost as quickly as they are captured. The Mikulski Archive for Space Telescopes distributes calibrated images to anyone with an internet connection. The European Southern Observatory maintains similar access for its instruments. Citizen scientists, equipped with backyard telescopes and determination, upload their own light curves to shared platforms. A generation ago, such openness would have been unthinkable. Today, it is routine. This transparency contrasts starkly with the secrecy that would likely accompany military or intelligence responses to confirmed alien contact. Astronomy defaults to openness for practical reasons. Peer review requires independent verification, and for philosophical ones, knowledge of the universe belongs to all. The investigation of 3I Atlas demonstrates how these principles hold even in cases that brush against humanity's most profound questions. Yet, openness carries challenges. Information now propagates globally in seconds. Legitimate results flow quickly through professional channels, but so too do distortions, exaggerations, and conspiracy theories. The same algorithms that amplify collaboration also reward sensation. In this sense, Atlas has been as much an information experiment as an astronomical one. Serious journals and institutional press releases emphasized its odd chemistry yet natural origin. Less careful outlets blurred speculation into fact, hinting at cover-ups or alien craft. The contrast illustrates the difficulty of maintaining public trust when evidence is subtle, but anxieties are vivid. Visuals complicate the picture further. Images from Hubble and Webb, stretched to reveal faint detail, take on eerie beauty. To a trained eye, they confirm cometary behavior. To a casual viewer, they may look like science fiction. Communicators face the challenge of contextualizing such imagery, reminding audiences that dramatic does not mean artificial. The problem is not deception but interpretation, how to prevent wonder from sliding into unwarranted conclusions. Containment, in this context, is less about physical samples than about information itself. Should certain astronomical discoveries be classified? Should data be restricted if anomalies emerge? The scientific community has generally answered with a firm no. Astronomy thrives on openness. Restriction would cripple collaboration, impede verification, and undermine public trust. The history of anomalous discoveries supports this position. Pulsars, initially nicknamed LGM for Little Green Men, were published openly, soon revealed as neutron stars. The wow signal of 1977 remains mysterious, yet all data have been available for scrutiny. Even Oumuamua, with its unusual shape and acceleration, was studied in the open. Secrecy has never been the scientific default. Citizen science provides another argument for openness. Amateurs have contributed real value to Atlas observations. Their images, though modest compared to professional telescopes, extend coverage and provide redundancy. This democratization of astronomy would collapse under containment policies. It thrives only because the sky belongs to everyone. The debate between containment and curiosity also plays out in planned missions. Space-based surveys like SphereX will map the sky in infrared, capturing interstellar visitors in unprecedented detail. Rubin Observatory's decade-long legacy survey of space and time is expected to detect hundreds of interstellar objects, turning rare encounters into routine catalog entries. These projects assume openness. Their design is predicated on shared archives, rapid alerts, and collaborative analysis. The precedent set by Atlas fast coordination, transparent data, distributed expertise, is shaping the institutional playbook for what comes next. Future risk assessment will draw on this precedent as well. Atlas has shown us what to expect from a natural interstellar comet: a safe trajectory, a coma driven by sunlight, spectra rich in carbon dioxide but within natural bounds. If future visitors deviate dramatically, alarm will be warranted. But the baseline assumption will remain: extraordinary claims require extraordinary evidence, and natural explanations must be exhausted before speculation prevails. The Atlas case also highlights the educational function of astronomy. Beyond scientific results, it demonstrates how knowledge is built, through cooperation, transparency, and skepticism in balance. Students watching the investigation unfold are learning not just about comet chemistry, but about the ethos of science itself. In this sense, Atlas is a teaching tool as much as a celestial visitor. At the psychological level, curiosity has won the day. The world has watched not in fear but in fascination. Unlike fictional portrayals of panic, the real response has been steady and measured. Scientists have pursued every possible observation. Agencies have shared results openly. The public, though exposed to sensational headlines, has largely engaged with awe rather than alarm. Atlas has become a case study not only in planetary science but in how humanity responds to the unknown. The lesson is hopeful. Even as speculation swirls, the dominant narrative remains scientific. Even as conspiracy theories proliferate, the evidence speaks louder. Curiosity has proven more powerful than fear. Containment, while a valuable principle in planetary protection, has been unnecessary here. Atlas passes at a safe distance, leaving only data in its wake. The true question is not whether we can contain it, but whether we can contain ourselves, our tendency to leap from anomaly to apocalypse, our hunger for meaning in silence. In the end, Atlas demonstrates that we can. We can balance caution with wonder, skepticism with imagination. We can recognize the difference between possibility and probability, between the story the evidence tells and the stories we tell ourselves. That balance, curiosity over fear, collaboration over secrecy, evidence over speculation, is the best preparation for whatever discoveries lie ahead. Part 10. Scale of the Cosmos and Our Signals. The story of 3I Atlas is inseparable from the scale of the cosmos itself. Its presence in our solar system today is the culmination of a journey across distances and times so vast that they strain human comprehension. To grasp what Atlas represents, we must place it against the backdrop of galactic history, where billions of years and trillions of kilometers blur into a single, relentless continuum. Astronomers suspect Atlas may hail from the Milky Way's thick disk, an ancient stellar population that formed when the universe was less than half its current age. The thick disk is the fossil record of the galaxy's turbulent youth. Unlike the thin disk, where the Sun resides in relative orderliness, The thick disk is populated by stars with tilted, eccentric orbits, scars of violent conditions long past. If Atlas emerged from such a birthplace, then its nucleus carries chemistry and mineralogy, forged in an environment radically different from the calm nurseries we know today. It is, quite literally, a fragment of deep galactic history, older than the solar system itself. The timescales involved invite awe. Imagine Atlas traveling for 5 billion years. In that time, massive stars have been born and gone supernova, scattering heavy elements across the galaxy. Entire planetary systems have arisen, some perhaps nurturing life, others ending in fire. On Earth alone, the Cambrian explosion, 5 mass extinctions, the age of dinosaurs, and the entire arc of human civilization have unfolded in what would amount to the final blink of Atlas's journey. From its perspective, our recorded history is the faintest scratch on cosmic time. Distances complete the humbling picture. Even at a blistering speed of 130,000 miles per hour, Atlas requires millions of years to cross meaningful swaths of the galaxy. Along the way, it has likely brushed past hundreds of stellar systems, its trajectory tweaked each time by gravity. Every encounter was silent, unwitnessed, but cumulative, a cosmic pinball game that steadily accelerated the object to its present velocity. What appears to us as impossible speed is, on galactic scales, simply the natural outcome of patience measured in eons. Its chemistry, dominated by carbon dioxide, acquires new significance in this light. This is not merely an odd comet with strange volatiles, it is a sample of alien geology. Each interstellar object delivers physical material from environments we cannot otherwise reach. Whereas starlight and spectra tell us about distant suns indirectly, Atlas gives us tangible evidence: frozen molecules, isotope ratios, volatile inventories born of another star's protoplanetary disk. It is as if the galaxy itself occasionally sends us sealed containers of its past, drifting across space until they cross our path. Now, set against this immensity, consider humanity's own signals. Since Marconi's first transmissions in the late 19th century, a sphere of electromagnetic noise has expanded outward from Earth. This radio bubble currently reaches about 120 light-years, a sphere encompassing perhaps a few thousand stars. Yet the Milky Way is 100,000 light-years across, containing roughly 400 billion stars. Our bubble is a microscopic ripple in an ocean. From most of the galaxy's perspective, we do not exist. Even within this bubble, our signals are faint. Television broadcasts and radar pings blur into background static within a few light-years. Only our most powerful planetary radars, aimed at asteroids or planets, shine brightly enough to be detectable across interstellar distances. To imagine that Atlas was drawn to us by these emissions is implausible. Its apparent antiquity predates our species, let alone our technology. It has been traveling since long before the first spark of human fire. The silence we encounter in SETI becomes less surprising when viewed through these scales. Even if the galaxy hosted thousands of civilizations, their signals would be extraordinarily difficult to detect. The inverse square law is unforgiving. Double the distance, and the brightness falls to a quarter. Unless civilizations beam vast energy directly at us, their voices are lost in the static. Interstellar communication is not impossible, but the energy requirements are daunting. To broadcast detectably across thousands of light-years would demand power outputs rivaling small stars. Even with tight beams, the engineering is staggering. These physical constraints explain why SETI has yet to find unambiguous signals despite decades of listening. The absence of evidence may reflect not absence of life, but the brutal economics of physics. Civilizations may choose silence not out of fear, but out of pragmatism. Shouting across the galaxy requires energy commitments that may be unsustainable, even for advanced societies. The same considerations frame interstellar travel. Accelerating a probe to even a fraction of light speed requires energy on scales beyond our civilization's reach. Propelling a large craft would consume more power than humanity produces annually. Natural objects like Atlas achieve their speeds not by engines, but by the accumulated nudges of gravitational interactions. The galaxy itself is the accelerator, given time enough to act. This perspective reshapes our interpretation of discovery. If planetary systems eject debris routinely during formation, then the galaxy should contain trillions of wandering bodies like Atlas. The Rubin Observatory, soon to begin its legacy survey of space and time, may detect several each year. What now feels extraordinary may become common. Each object will represent another data point, another opportunity to expand our sample of galactic chemistry. The diversity we've observed so far, elongated, Oumuamua, comet-like Borisov, Colorado, 2, rich Atlas, may prove to be only the beginning. The temporal dimension adds still more nuance. Over billions of years, the galaxy's chemical composition has steadily enriched, as stars forge heavy elements and recycle them through supernovae. Objects that formed early reflect a leaner, metal-poor galaxy, with different volatile balances than modern systems. If Atlas indeed originates from this earlier epoch, its carbon dioxide dominance may be less anomaly than signature of ancient chemistry. Studying such bodies gives us direct insight into how the galaxy itself evolved. They are time capsules, carrying the fingerprints of an earlier cosmos. The juxtaposition is striking. On one side, Atlas, ancient, immense, a wanderer across billions of years. On the other, humanity's radio bubble, a fragile whisper, barely more than a century old. We are newborns in cosmic time, broadcasting into a silence that is less mysterious once we grasp the scale of the stage. Our faint transmissions have reached only the nearest stars. Atlas has crossed the galaxy. Our history spans millennia, its voyage, billions of years. And yet both stories converge here, in the present, in this brief overlap, where human instruments catch sight of an interstellar traveler. Atlas does not need to be artificial to be profound. Its significance lies in the way it bridges scales, connecting our fragile signals with the galaxy's deep history, reminding us of both our smallness and our potential. The lesson is double-edged. The cosmos dwarfs us, humbles us, and reminds us that our presence is still negligible on galactic terms. But it also shows that even in our infancy, we can detect, measure, and interpret these vast processes. Our signals may be faint, but they exist. Our reach may be short, but it grows. Atlas's visit underscores both our limitations and our progress. It teaches us to think in billions, to situate our tiny bubble of civilization within a galaxy that has been evolving for eons. As this investigation nears its end, the scales of the cosmos provide perspective. Atlas is a comet, strange, yes, but natural, bound by the same physics as everything else. Yet by studying it, we glimpse epochs and neighborhoods far beyond our own. We learn to place our radio bubble, our technologies, and our questions into context. And in that context, the silence of the universe becomes less a paradox than a reminder. The galaxy is vast, our history short, and the conversation has only just begun. Part 11. Hope in Silence and Data. Perhaps the greatest gift 3i Atlas offers humanity is not hidden in speculation about alien engineering or cosmic surveillance, but in its quiet obedience to the laws of nature. It arrived precisely when predicted, traced the trajectory celestial mechanics demanded, and departed again into the interstellar dark without disrupting a single sunrise on Earth. In a century defined by uncertainty, climate pressures, geopolitical tensions, and fragile economies, there is something deeply reassuring about a cosmic visitor that behaves exactly as physics decrees. That reassurance is not trivial. It represents the triumph of science over anxiety, of careful observation over unfounded fear. When Atlas was first detected, streaking inward at extraordinary speed, it might have been tempting to imagine disaster. Yet within weeks, Astronomers around the world had calculated its orbit with precision, measured its chemistry, and ruled out any threat. This was human knowledge at its finest: rapid, transparent, collaborative, and calm in the face of mystery. The scientific harvest has already exceeded what many discoveries yield in decades. Atlas's coma, unusually dominated by carbon dioxide, challenged long-standing assumptions about cometary chemistry. Conventional wisdom held that water ice should dominate activity at the distances where Atlas was observed. Webb's infrared spectra forced researchers to consider new models, perhaps formation near the CO2 snowline of its natal disk, or long-term radiation processing that altered surface layers while leaving deeper volatiles sealed. Either explanation expands our understanding of icy bodies across stellar systems. These insights reach far beyond cometary science. The ratios of volatiles in such bodies shape theories of planetary formation and migration. If carbon dioxide-rich environments were once common, then planets forming in those regions might inherit different inventories of gases, with consequences for climate and habitability. By studying Atlas, we refine our search strategies for life-bearing worlds. Even a single anomalous comet becomes a probe into the conditions under which planets and perhaps biospheres emerge. Institutionally, the Atlas campaign has demonstrated how far astronomy has advanced in coordination. Discovery by the Atlas survey in Chile triggered immediate notification to the Minor Planet Center, which collated positions from telescopes worldwide. Hubble was reassigned within days, Webb within weeks, and observatories from Hawaii to the Atacama contributed complementary views. Such responsiveness would have been impossible a generation ago. The architecture of modern astronomy, automated alerts, open archives, global coordination, is itself a quiet triumph. Equally significant is the decision to make data freely available. Hubble and Webb images, ground-based spectra, and light curves all flowed into public repositories. Researchers in any country, amateurs with modest equipment, and even students in classrooms could access the same files as leading professionals. This democratization embodies the conviction that cosmic knowledge belongs not to one nation or institution but to humanity as a whole. It also creates resilience. Extraordinary claims must withstand the scrutiny of thousands of independent eyes. That openness is vital when confronting phenomena that could, in principle, challenge our deepest assumptions. If one day an interstellar object reveals genuinely anomalous signatures, the precedent of transparency established here will guide how we separate error from reality, artifact from discovery. Shared data is the best antidote to panic, rumor, and premature conclusions. The communication challenge remains real. In an era where information spreads instantly, careful science must compete with viral speculation. Atlas provides a case study in how to navigate this landscape. Professional institutions consistently emphasized both the object's peculiarities and its conformity to natural expectations. They acknowledged uncertainty, but resisted sensationalism. Less reputable outlets sometimes blurred the line, presenting speculation as fact or suggesting conspiracies. Yet the steady voice of science press conferences, explanatory graphics, live tracking websites kept the core narrative intact. Millions learn not just about Atlas, but about spectroscopy, orbital mechanics, and the structure of the galaxy. Public engagement has been remarkable. Amateur astronomers tracked the object's faint motion. Students analyzed brightness data as part of coursework. Citizen science platforms recruited thousands to help process images. For many, Atlas was the first interstellar body they had followed in real time. This participatory science strengthens the bond between discovery and society, ensuring that cosmic wonders are not confined to professional circles. Speculation also played its role. The what-ifs, probes disguised as comets, silent seeds drifting through space, captured imaginations, sometimes productively, sometimes misleadingly. At its best, such speculation pushes researchers to design tests, What signatures would artificial activity produce? How can we distinguish unusual chemistry from exotic engineering? At its worst, speculation is confused with fact, generating needless anxiety. The key is clarity. Hypotheses are valuable when they sharpen our questions, harmful when they masquerade as conclusions. Science advances by balancing these impulses. Creative hypothesis and rigorous testing, imagination and evidence, are not enemies but partners. The investigation of Atlas illustrates this rhythm. Early anomalies prompted speculation. Subsequent measurements constrained possibilities. Evidence accumulated until the natural explanation stood robust. What began as mystery resolved into understanding not by eliminating imagination, but by channeling it into testable paths. This arc provides reason for optimism. If we can unravel Atlas, we can unravel stranger phenomena yet to come. Rubin Observatory will soon detect hundreds of interstellar objects. Each will add to our dataset, revealing population-level trends. Some may be water-rich, others volatile-poor, a few as exotic as Atlas or stranger still. With each discovery, our capacity to distinguish the normal from the extraordinary will sharpen. The broader context is equally powerful. Every interstellar visitor is a messenger from another stellar nursery, carrying frozen relics of processes we cannot otherwise sample. Atlas connects us to environments billions of years old, to chemical pathways shaped before Earth formed. It is not just a comet, it is a tangible piece of the galaxy's memory. And in its silence lies hope. Atlas did not crash into Earth, did not reveal hostile intent, did not upend our civilization. Instead, it reminded us of the power of patient observation, the strength of collaboration, and the beauty of physics unfolding exactly as predicted. In an age crowded with existential worries, the knowledge that the cosmos can still deliver reassurance is itself profound. Perhaps that is the final lesson. The unknown need not be feared. With the right tools, the right institutions, and the right philosophy, mystery becomes opportunity. Atlas entered as an object of speculation and left as a case study in science done well. By replacing fear with understanding, it offered us the most valuable gift a cosmic visitor can provide, the demonstration that even the strangest phenomena can yield to curiosity, collaboration, and evidence. Part 12. Good night, Cosmic Messenger. As 3I Atlas recedes into the depths of space, fading with each night into the backdrop of stars from which it emerged, what remains is not the object itself but the images, spectra, and data that will endure long after its glow has vanished from our instruments. Hubble's portraits show a delicate star-like blur wrapped in the faint veil of a carbon dioxide coma, as if the universe had hung a fragile ornament against an infinite black canvas. Webb's infrared gaze adds further depth, spectral lines etched across its detectors, each one a syllable in the ancient chemical language Atlas carries from a nursery light years away. Together, these records become the enduring footprint of a traveler already beyond our reach. The trajectory plots are just as eloquent as the photographs. Smooth arcs across digital charts trace Atlas's flight through our neighborhood, a descent past Mars's orbit, a brief swing around the Sun, and then a long outbound path toward the realm of the giants, before vanishing once more into interstellar night. There is serenity in these curves, the inevitability of celestial mechanics, untroubled by the chaos of human events. Politics may shift, economies may falter, but Atlas obeys rules older than Earth itself. In an age saturated with artificial urgency, there is something profoundly comforting about a phenomenon that unfolds exactly as the equations demand. The answer to our central question, what is the worst-case scenario, has turned out to be refreshingly mundane. No catastrophe loomed, no alien fleet followed, no orbital disruption threatened our survival. The worst case is simply nothing at all. Atlas will depart as it arrived, silently, safely, predictably. Yet calling this outcome mundane misses the deeper point. that we can predict the motion of an object that has traveled for billions of years, that formed around a star we have never seen, and that carries chemistry from epochs before Earth existed. This is a triumph. It testifies to the universality of physical law, to the power of science, to reach across gulfs of time and distance. Natural does not mean uninteresting. Atlas's odd chemistry, a coma rich in carbon dioxide compared to water, challenges assumptions about what comets should look like. Its suspected thick disk origin situates it in a galactic population far older and more chaotic than our own thin disk neighborhood. These properties are not curiosities to file away. They are clues. They expand models of planetary formation, force revisions of cometary evolution, and diversify our picture of how materials cycle through the galaxy. Papers written today will be cited for decades as researchers integrate Atlas's anomalies into broader theories of galactic chemistry. Speculation, too, has played its part. Over these months, we have entertained possibilities ranging from hidden probes to cosmic seeds, from ghost civilizations to dark forest strategies. None are supported by evidence, and the data consistently reinforce the natural interpretation. But the exercise has value. It reminds us how imagination and evidence interact, how hypotheses can sharpen our ability to test, to measure, to define the boundaries of the possible. The universe, after all, has proven plenty strange on its own. Quantum entanglement, pulsars, black holes, accelerating expansion. We do not need alien machines disguised as comets to sustain wonder. Nature is extraordinary enough. How, then, should we say farewell? Not with ominous chords or swelling triumph, but with contemplative music, something like Holst's The Planets, or Barber's Adagio for strings, soundscapes that blend grandeur with melancholy. They capture the paradox that Atlas is both mystery and clarity, both alien and familiar, both fleeting in its visit and eternal in its adherence to natural law. The tone we leave behind should invite reflection rather than fear, wonder rather than alarm. Throughout this journey, we have worked to mark the boundary between data and conjecture, between what we know and what we imagine. That distinction is more than intellectual honesty. It is a necessity in an age where misinformation spreads faster than corrections. Atlas is not an omen of invasion or doom. It is a test case in how evidence dispels anxiety, how international collaboration replaces panic with understanding. The real danger was never Atlas itself, but the human tendency to fear the unknown. Patient observation has proven the antidote. The epilogue to this investigation should point viewers not to conclusions, but to resources. NASA's mission pages, the Space Telescope Science Institute archives, peer-reviewed papers, and even citizen science projects remain publicly available. These repositories embody more than bibliography. They symbolize the democratic spirit of modern astronomy, discoveries shared openly, data released freely, and the cosmos treated as common heritage rather than proprietary asset. Such transparency is the best preparation for future encounters, whether with ordinary comets or with something stranger. Indeed, the promise of future discoveries already beckons. The Rubin Observatory will soon transform interstellar objects from rare surprises into routine catalogue entries. Some cousins of Atlas may prove even more chemically exotic. Others may conform neatly to expectations, providing the statistical weight needed to distinguish patterns from outliers. Each new arrival will refine our picture of galactic evolution and planetary birth. Each will be another messenger, carrying secrets from stars we may never reach. The credits for this chapter rightly belong not to a single hero, but to a network: survey telescopes, orbital observatories, archive managers, citizen scientists, and the thousands of anonymous contributors who turned faint photons into understanding. Atlas was never owned by one nation or institution. It was studied collectively, across borders, disciplines, and languages. That is perhaps its deepest lesson. When humanity confronts the unknown, our best tools are not secrecy or fear, but collaboration and curiosity. Now Atlas fades, its coma thins, its nucleus shrinks to invisibility, and its trajectory carries it outward at unyielding speed. It leaves behind no threat, no wreckage, no beacon, only knowledge. And that knowledge is enough. A reminder that science can tame uncertainty, that nature can surprise without terrifying, that the universe still holds wonders waiting for us to notice. The silence that follows is not empty. It is a pause, pregnant with expectation. Somewhere out there, another interstellar traveler is already inbound, carrying its own chemistry, its own anomalies, its own story. When it arrives, we will be ready with instruments tuned, archives open, and imaginations prepared. The screen fades to black. Atlas disappears into the star field, indistinguishable once more from the background that birthed it. Its journey continues, unobserved but unstoppable. Ours continues too, now enriched by the brief encounter. Good night, Cosmic Messenger. Thank you for the data, the lessons, and the reminder that the universe is stranger, richer, and more beautiful than our fears allow. Safe travels across the galactic wilderness. May your cousins one day cross our path again, bringing fresh puzzles, fresh knowledge, and fresh reasons to look upward with wonder.